Here's a ridiculous little test. Take a giant open model, squeeze its weights down to 4 bits, then drag the file onto an RTX 5090. It doesn't load slowly. It doesn't load at all. The card has 32 gigabytes of memory. The model may need hundreds. Now move that same model into this tower. NVIDIA says its new DGX station can hold models with up to 1 trillion parameters. The number doing the heavy lifting is 748 gigabytes of coherent memory. That sounds like 23 RTX 5090s, somehow folded into one PC. It isn't. The memory comes in 2 very different speeds. The 20 petaflop number uses very specific math, and one system you can order today starts at about $94,000. So this is not the ultimate gaming PC. It is a private AI data center that happens to stand beside a desk. And once you see that, the whole machine makes a lot more sense. Start with the problem it was built to solve. A language model is mostly a huge collection of numbers called weights. To generate text quickly, the machine needs those numbers close enough to the processor that it can read them over and over. You can spill some of the model into normal system memory. You can even stream pieces from storage. But every slower hop costs time. For fast inference, capacity and bandwidth both matter. The capacity math is simple. A 70 billion parameter model stored at 16 bits needs about 140 gigabytes just for raw weights. Cut that to 4 bits, and the raw number falls to about 35 gigabytes. That is why quantization feels like magic. The model is not getting smaller because it learned less. We are storing each number with fewer bits. Now scale that to 671 billion parameters. At 4 bits, the raw weights alone are about 336 gigabytes. Add file metadata, runtime buffers, and the model's working memory. And a 32 gigabyte graphics card is not even in the conversation. Then context starts growing. As the model reads your prompt and writes its answer, it keeps a working record called the key value cache. The exact size depends on the model, the cache precision, the context length, and how many requests run at once. There is no honest universal number, but the direction is easy to understand. Longer context and more simultaneous users require more memory. A model that barely fits on paper can run out of room in the real workload. That is the wall. NVIDIA's answer is not just add more VRAM. It is stranger and more useful. Inside the GB 300 superchip are 2 memory neighborhoods. Right next to the Blackwell Ultra GPU sits 252 gigabytes of HBM3e. It can move data at up to 7.1 terabytes per second. This is the fast neighborhood. Beside the 72-core Grace CPU sits another 496 gigabytes of LPDDR5X. That pool is much larger, but its quoted bandwidth is 396 gigabytes per second. Still fast, just nowhere near HBM. NVLink C2C connects the CPU and GPU sides at 900 gigabytes per second. The system keeps them coherent, which means the processors can work with one shared address space instead of treating every transfer like a package crossing a slow, separate border. Add the 2 pools and you get 748 gigabytes, but coherent does not mean identical. Think of it as one building with a fast workshop and a giant warehouse. The workers can reach both without leaving the building. You still want the parts they touch constantly inside the workshop. That distinction is missing from most giant memory headlines. DGX station has enormous coherent capacity. It does not have 748 gigabytes of HBM. And this is where we can replace hype with a calculator. In the terminal, I'll ask a tiny script to budget a 671 billion parameter model at 4 bits. The raw weight math returns 335.5 gigabytes. I'll add a clearly labeled 10% allowance for format and runtime overhead. That moves the illustrative load to roughly 369 gigabytes. Against 748, it fits with room left over. Run the same calculation for 1 trillion parameters. Raw weights are 500 gigabytes. With that same allowance, the budget becomes roughly 550. It still fits by capacity. That does not prove it will be fast. It proves one thing only. The weights can fit inside the advertised memory budget. Real speed depends on the model, where its hot tensors live, cache size, software, batching, and the precision actually used. This is also why 20 petaflops needs a label. NVIDIA says up to 20 petaflops of FP4 tensor performance with sparsity. FP4 stores numbers in 4 bits, and sparsity can skip work when values follow the supported sparse pattern. That peak is useful for comparing the intended AI path. It is not 20 petaflops for every operation, every model, or every framework. If someone gives you a giant compute number without precision and test conditions, the number is wearing a Halloween costume. So what does this machine genuinely unlock? First, model capacity. Teams can work with models and datasets that simply do not fit on ordinary workstations. Second, privacy. A hospital, bank, research lab, or defense contractor may have data that cannot be sent to a public API. Local inference is not just a preference there, it may be the requirement. Third, shared infrastructure. NVIDIA's multi-instance GPU feature can divide the GPU into as many as 7 isolated instances. ConnectX-8 networking can link systems at up to 800 gigabits per second. This tower can act less like one person's PC and more like a small team's local compute service. And fourth, control. Long-running agents can stay close to private tools, private files, and internal applications without paying a per-token bill for every experiment. That sounds wonderful. Now look at the other side of the decision. An exact DGX station listing starts at $94,011.50 as of this research. MSI's WS300 specification uses a 1600-watt power supply and liquid cooling rated for up to 1400 watts across the CPU and GPU. The Grace CPU is ARM-based, and the current workstation ships with Ubuntu and NVIDIA's developer stack. This is enterprise infrastructure. The tower shape is almost a prank. For a hobbyist, a solo developer, or a team whose models fit into 32 or even 128 gigabytes, buying this much headroom is like renting a warehouse for one bicycle. NVIDIA's smaller DGX Spark currently offers 128 gigabytes of coherent memory for a listed price of about $4,700. A consumer or professional GPU may be the better choice when the model fits in its faster dedicated memory. And cloud compute is often the smarter answer when the workload is occasional, changes quickly, or needs a large cluster for only a few hours. DGX Station wins when 3 things happen together. Your model, context, or concurrency genuinely needs hundreds of gigabytes. Your data or workflow needs to stay local, and you will use the machine enough that owning the capacity makes more sense than renting it. Miss any one of those, and the giant number may be solving the wrong problem. So yes, NVIDIA put 748 gigabytes into a desk-side machine. That part is real. The important story is not that one magical PC replaced the cloud. It is that CPU memory and GPU memory are being pulled into one coherent system, large enough to make private frontier-scale experiments practical for organizations that can justify the cost. 32 gigabytes is a fast room. 128 is a serious local lab. 748 is a private loading dock for models that used to arrive by data center. Pick the smallest rung that fits the model, the context, the users, and the rules around your data. Buy the memory you can prove you need, not the headline.